In this problem, we are given an array where every number represents the height of a vertical bar. Each bar has a width of 1. After rainfall, water may get trapped between these bars. Our task is to calculate the total amount of trapped water. For example, height equals 4, 2, 0, 3, 2, 5. The answer is 9. So here we can see how. If this is our height, then water can get trapped into. Let me log in here. So this is our height 4, 2. So let me create some kind of structure here. So first height is 4. So 4 sticks are there. Then next height is 2. Then next height is 0. So nothing is there. The next height is, so let me put a dash. Next height is 3. Then next height is 2. Finally we have 5. So if rainfall comes, if rain happens, then how much water can be stored in this? So water will cover only till here, and this will also be filled. This portion will also be filled. So here we can see 2 units will be filled. These 2 units plus 1 unit here. So these 3 units, this 1 unit will be filled. Then this 3 unit will be filled. So 3 plus 1 is 4. Then 1 unit here will be filled. That is 5. Uh, Actually, we also have this bigger stick. So let's calculate again. So this much water will come up to this row number 5. From row number 8 to row number 5, water will fill this container. So here 2 units will be filled. Then here 1, 2, 3, 4. 4 units will be filled. Here 1 unit will be filled. So 2 plus 4 plus 1, that is equal to 7. Then here 2 units will be filled, 1 and 2. So total 9 units are filled. So that is our answer. Um, let's think about this. Water can only be trapped when there is a sufficient tall bar on both sides. For every position, the amount of water stored above it depends on tallest bar on its left and the tallest bar on its right. So this is a very big intuition for every position. For every position, water filled depends upon first the tallest bar on its left and the tallest bar on its right. The water level at that position is limited by the shorter of these two boundaries. Therefore, water at index I equals minimum of maximum height on left, comma maximum height on right, and minus current height. For example, left maximum equals 4 and right maximum equals 5 and current height equals 2. Then water equals min of 4,5 minus 2 and that is equals 2. The shorter boundary determines the water level because water would overflow from that side. Now let us discuss the brute force approach. So for every index we can do these three things. Search towards the left, search towards the right and find tallest bar and calculate the trapped water at that index. The formula is this. That is minimum of left maximum, right maximum minus height of at that position, height I. However, finding the left and right maximum for every index requires repeatedly scanning the array. So time complexity becomes O of n power 2 and space becomes O of 1 because we are not using any external array. We are just using a few more variables. So space is constant, but time complexity becomes order of n square because for every index we are scanning the array again and again. So n indices are there and n times we are scanning the array. So n multiplied by n is n square. We can pre-compute. So better approach can be pre-compute left max I and right max I. Then for every index water is simply by the previous formula min of left maximum and right maximum. But this has complexity of time complexity will remain as On, not remain, it will improve from previous On square to On because we are scanning the array only twice or once to calculate these arrays left max and right max. But space complexity will increase from O1 to On because we need to maintain two extra arrays. So the question is, can we solve it in a linear type and constant space? So this is the best approach, two-pointer approach. We place one pointer at each end of the array. So left equals 0 and right equals n minus 1. And we maintain left max and right max. So these represent the tallest bars encountered from the left and right sides. The important observation is when the left bar is shorter than the right bar, the amount of water at that left position depends only on left max. Why? Because the right side already has a bar at least as tall as the current left bar. So this is the important observation that when left bar, this at index 1 is shorter than the previous left bar, then we don't need to maintain this. We just need to maintain the tallest from the left side, and similarly for the right side. Therefore, we always proceed the shorter side. So let me explain once again. This is the important observation. When the left bar is an important observation. When the left bar is shorter than the right bar, the amount of water at the left position depends only on the left max, because the right side already has a bar at least as tall as the current left bar. Similarly, when the right bar is shorter, the water at the right position depends only on right max. Therefore, we always process the shorter side. So let us write the pseudocode, then we will get to understand it more easily. So we left equal to 0 and right equals length of height minus 1. Then we initialize left max, right max and total water. Then we run this loop. So while left is less than right, if height of left is less than height of right, then we check if height of left is greater than equal to left max. Then left max equals height left. Else, if height of left is less than left max, then total water equals left max minus height of left. And then we do left plus 1. And otherwise, we do the similar thing for the right side. Just to left with right. So instead of left, right will come. Instead of left, right will come. We do right max equals height right. Else, total water plus equals right max minus height right. And then we do right minus equal to 1. We move one unit backward. Then finally return the total water. So let us now quickly write the Python solution. Here we initialize left max, right max and trapped water. Then we start the loop. Then we check the if my height left is smaller or height right is smaller. Then we check if height left is smaller than height right. Then we check if height left is greater than or equal to left max. If it is, then we update the left max and continue. Else, we update the trapped water. And if height of left is greater than height of right, that is the else condition. Then we do a similar thing on the right side. We check if height of right is greater than right max. If it is, then right max equals height of right. Else, trapped water plus equal right max minus height of right. And finally, we decrease right by 1, and we return the tapped water. So this will be more clear once we look at the dry run. So this is our height, and initially these are the values. Left equal to 0, right equal to length of this array is 6, so 5. Left max and right max are 0, 0 and water equals 0. So at step 1, we have height left equals 5 equals 4 and height of right equals 5. And since 4 is less than 5, we process the left side. So process the left side, and then we see that height of left is greater than or equal to left max. So we go inside this and update our left max. So our left max will become equal to 4 and left will increase by 1 equals 1. So again we check if left is height of left will have a different value now. Now height of left becomes 2 and right is 5. So again we process the left side. Now left max will remain as 4 because it is less than left max. So I will go to this step. So my trapped water will become by this formula left max minus height of left. So left max is 4 minus 2 equals 2. So 0 plus is plus equal to. And then my left will become equals 2. Now my height of left and right will again update. Height of left will become equal to 0. I will again process the left side. This time again it is less than the max height. So my trapped water will increase. So water will become equals 2 plus max left max is 4. So 4 minus left equal to 6. And left will become equal to 3. Now again I will check height left and height right. So height left is now 3. Again I will process the right side, so left side, and water will become my left max was equal to 4 and height left is 2. So again I will increase the water. Sorry, my height left is 3. So again I will increase the level of water. So it will be 6 plus 4 minus 3 equals 7. And left will become 4 this time. So in this way you can complete and we will arrive at the solution answer equal to 9. So question can be, why do we process the shorter side? Suppose height of left is less than height of right. The right side already provides a boundary taller than the current left bar. Therefore, the amount of water at the left position is controlled by the tallest bar and counted on the left. We do not need to know the exact maximum bar farther to the right. The reverse logic applies when the right bar is shorter. This is the key reason the two-pointer approach works. Let us run the solution once. Now let us submit it. Okay, so all the test cases pass. Finally, let us discuss the time complexity. Time complexity is obviously On because we are scanning the array only once, and the space is constant, that is O1, because we are not maintaining any extra array. We only store a few variables. Now let us discuss the common mistakes. First is adding negative water. Never directly add left max minus height left without checking whether left max is greater. Update the maximum when the current bar is taller. Second mistake is processing the taller side. The shorter side gives a confirmed boundary and can safely be processed. Third is mistake confusing width with height. Every bar has width 1. So the trapped water at any an index is simply the height difference. Counting water above boundary bar. A bar that creates a new maximum does not trap water above itself. So for every position, water equals minimum of the tallest boundaries minus the current bar height. Instead of building separate left and right maximum arrays, we use left pointer, right pointer, left maximum, right maximum. We always process the shorter side. This gives us on time and O1 extra space, and that is optimal solution for trapping rainwater.